Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
1760, John Michell on the means of discovering the distance, magnitude, etc. of the fixed. The year 1760 marked a pivotal moment in the pursuit of understanding the cosmos. Prior to this, the sheer vastness of space posed a formidable challenge to astronomers. Determining the distances and sizes of stars, fundamental to comprehending the structure and scale of the universe, remained largely speculative. Existing methods, primarily relying on parallax measurements, were severely limited. Stellar distances, often immense, rendered the minuscule shifts in a star's apparent position, caused by Earth's orbit, exceedingly difficult to measure with the available technology. This is where John Michell's on the means of discovering the distance, magnitude, etc. of the fixed stars entered the scene, proffering a novel and ingenious approach to tackle this persistent challenge. The intellectual problem Michell grappled with centered upon the limitations of contemporary techniques. Parallax, a geometric method dependent on observing a star's apparent shift against a background of more distant objects, was hampered by instrumental inadequacies and intrinsic cosmic scales. The inability to accurately gauge stellar distances crippled efforts to determine stellar luminosity, a key factor in understanding their intrinsic brightness and the energy they emitted. The lack of reliable methods hindered astronomers' ability to map the universe, limiting an expansion of our understanding of its size and composition. This directly challenged investigations into the fundamental nature of stellar objects and the distribution of matter throughout the cosmos. Michell's groundbreaking contribution lay in his innovative application of statistics and probability to the analysis of stellar distribution. He proposed that by examining the spatial arrangement of stars, specifically looking at the frequency of apparent close pairings, it would be possible to infer information about their distances and physical relationships. His core methodology hinged on the notion of chance alignments. He posited that if stars were randomly scattered across the sky, the likelihood of two or more appearing close to each other would be predictable and calculable. Any significant deviation from this expected randomness would then, he argued, suggest a physical association. Michell's work was deeply rooted in the scientific framework of his time, particularly the principles of Newtonian physics and the nascent field of probability theory. His approach drew influence from earlier works, such as those of Edmund Halley on the proper motions of stars, demonstrating the movement of stars relative to each other. Halley's observations provided a foundation for understanding that stars were subject to motion and that they might have physical connections. Michell expanded upon this by introducing a statistical framework for assessing the likelihood of such connections. The mathematical arguments presented in Michell's work were sophisticated for the era. He employed probability calculations to assess the likelihood of chance alignments, establishing a baseline against which observed stellar pairings could be compared. The core assumption revolved around the idea of a uniform distribution of stars. If stars were distributed randomly through space, the calculations would permit a projection of the frequency with which stars would, by chance, appear near one another. Any significant deviation from this expectation could be attributed to a physical connection between the stars, or, perhaps, an error in the foundational model. This involved complex geometric reasoning to estimate the expected number of close pairs within a given area. Michell's work provided concrete examples of how to identify binary star systems. He demonstrated that the observed frequency of close stellar pairs in the constellation of the Milky Way significantly surpassed the expected number to arise purely from chance. This suggested that these stars enjoyed a physical bond, orbiting each other. The discovery offered a methodology for identifying them as distinct physical entities and, by studying their movements over time, estimating their distances and, subsequently, their mass. The direct implications of Michell's work were immediately relevant. It provided a new means to investigate the nature of binary stars. It suggested that these pairs were not merely chance alignments, but physically related systems. This would, in turn, aid in the development of new methods to measure stellar distances, complementing the limited capabilities of parallax. The exploration of binary star systems offered an opportunity to extend the reach of astronomical investigation beyond individual stars, delving into the nature of gravitational interaction. Furthermore, this approach laid the groundwork for later statistical astronomy, offering a new way to understand the distribution of stars across the Michell's statistical approach to understanding astronomical phenomena foreshadowed later developments in astrometry and statistical astronomy. His work indirectly paved the way for subsequent research on star clusters and galaxies, offering an early framework for analyzing larger-scale astronomical data. His insightful approach, the application of probability to astronomical problems, revolutionized the means by which astronomers approached the challenging task of understanding the cosmos. Michell's work offered a novel synthesis of Newtonian mechanics and probability theory, providing an innovative methodology for understanding the structure and scale of the universe. 1760 John Michell on the means of discovering the distance, magnitude, etc. of the fixed. Section 2. Analyzing stellar relationships. Michell's investigation of stellar distances and the concept of stellar magnitude constitutes a cornerstone of his 1760 work. His approach, though constrained by the observational limitations of his era, initiated the application of statistical methods to astronomical questions. He turned his attention to the properties of binary star systems, recognizing these as keys for unlocking the secrets of cosmic distances. The core of his methodology revolved around the study of these dual star systems. He reasoned that if two stars appeared close together in the sky, a significant question arose regarding whether their proximity was accidental, a chance alignment, along the line of sight from Earth, or indicative of a physical association governed by gravitational forces. Michell tackled this problem by utilizing probability theory. He calculated the probability of observing stars in close proximity purely by chance. He began by computing the likelihood of observing two stars within a certain angular distance of each other, assuming a uniform distribution of stars across the celestial sphere. To achieve this, he had to determine the number of stars visible to the naked eye, accounting for variables like stellar magnitude, which affected how bright a star appeared from. The mathematical argument proceeded systematically. Michell considered the area of the sky within a certain angular radius of a given star. If stars were randomly scattered, then the probability of another star appearing within that area was proportional to the area itself. Specifically, the probability was equivalent to the ratio of the area of interest to the total area of the celestial sphere. Michell then extended this concept. He computed the probability of finding a second, a third, or even more stars within a certain angular distance of the first. By comparing these theoretical probabilities with the observed frequency of close star pairs, Michell could infer whether the observed pairings was simply the result of chance or implied a physical connection. He thereby advanced the idea that the pairing of stars could be due to mutual gravitational interaction, though the concept of gravity in this context was not yet fully understood. Michell's statistical method required a profound understanding of probability, a discipline that was still emerging as a formal branch of mathematics. He was able to demonstrate that the probability of two stars appearing close to each other purely by chance was exceedingly low. He found that the frequency of observed close pairs far exceeded what could be predicted by chance alone. This led him to the conclusion that these stars were in fact physically associated, orbiting each other. This was, in effect, the first rigorous evidence for the existence of binary star systems, decades before their orbital characteristics could be accurately measured. Nevertheless, Michell's methodology suffered from several limitations. The accuracy of his calculations depended critically on the accuracy of star catalogues available at the time. These catalogues, limited in their scope and precision, could introduce errors into his analysis. Furthermore, the limitations of observational technology meant that only the brightest stars were available for study. The assumption of a uniform distribution of stars, though reasonable as a first approximation, clearly oversimplified the complexities of stellar distribution. The effects of interstellar absorption and the intrinsic variations in stellar brightness also posed challenges. These uncertainties, however, far from invalidating Michell's approach, actually highlighted its value. He explicitly acknowledged these limitations, viewing them as areas for future refinement and better observational data. Despite these limitations, Michell's contribution proved revolutionary. His work provided the intellectual framework that motivated later astronomers, including Sir William Herschel. Herschel substantially expanded on Michell's work. Herschel's cataloguing and observations of binary stars, undertaken in the late 18th century, directly built upon Michell's insights. Herschel would eventually measure stellar distances using parallax data, providing the first accurate measurements of stellar distances and proving Michell's hypothesis about binary systems. Michell's statistical approach, though it concerned binary star systems, was far-reaching. His core idea, the application of probability to understand the distribution of celestial objects, foreshadowed developments in modern astrophysics and cosmology. His work implicitly paved the way for the study of star clusters, galaxies, and the large-scale structure of the universe. Modern statistical methods, used to analyze enormous astronomical datasets, draw on Michell's fundamental insight. His method of investigating the likelihood of a distribution of objects and calculating if they vary from randomness still applies today. Modern astronomers consider the spatial distribution of galaxies and the clustering of matter on vast cosmic scales. These investigations employ statistical techniques originally pioneered by Michell. Michell's influence extended beyond astronomy. His work was known to Henry Cavendish, who was instrumental in the 1798 Cavendish experiment. This experiment, which measured the gravitational constant, was performed decades after Michell's death. The experiment's design utilized a torsion balance, a delicate instrument that would have been impossible without Michell's earlier designs. Furthermore, the importance of measuring gravity led Cavendish to adopt the same probabilistic framework that Michell had used to study stars. Thus, the influence of Michell's ideas on scientific progress goes beyond the realm of astronomy. The legacy of Michell's work is multifaceted. His pioneering application of statistical methods to astronomy transformed the way scientists approached the cosmos. His insights regarding binary star systems, though initially grounded in limited data, formed the basis for key discoveries. These discoveries subsequently changed our understanding of stellar evolution. The impact transcended its time, influencing the work of Herschel, Cavendish, and countless others. His efforts initiated the process of systematically mapping and cataloguing the sky, a project that continues to this day. Through his work, Michell profoundly changed our vision of the universe, from a collection of isolated stars to a dynamic, interacting system.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.